All right, we're going to be looking at quadratic functions. So our learning intention states that I will learn how to graph non-linear relationships between two quantities. Remember the two quantities, the quantities are the two things we put on the axes. So we have the y-axis and the x-axis. And then if we're putting time versus speed or whatever, those are considered quantities, all right? And then it's nonlinear because it's not a straight line anymore. We're looking at a quadratic function today. So for my success criteria, I will say understand the relationship between two quantities on a quadratic graph. We know what a quadratic graph is, all right? We're about to look into it. Quadratic graph is generally represented by a semicircle or a parabola. The entire U or the N-shaped looking graph is called a parabola, all right? I put that word in the chat so we so that everyone knows how to spell that word. It's called a parabola. And go ahead and Google that word. You could see what I'm talking about. And then one of the other success criteria is I can successfully graph a quadratic story. So again, we're gonna be looking at some stories, and then we're gonna have to draw the graph of it. All right, so the first thing we're gonna do is we're gonna watch this video. This is one of my really good friends, and she made a video, and I think it's very helpful. Like it's very well explained. So we're gonna watch this video, and we're gonna look at how she works out some of the questions.
Relationships. Let's begin by watching a video of a jumper who is completing a world record dive into a swimming pool filled with water beneath him. As you are watching, I want you to think, how would the graph of this dive look?
Take those 6 and add 1 more. That's right, 7. If you guys are ready for 7 balls, let me hear you say, yeah.
Yeah.
I mean, this is great. I came out of it really well. I'm proud. Good dive. I'm glad she's done. You know, but I can have a good meal and some sleep.
We just observed a graphing story that represents a diver's change in elevation over time. This time, I'm going to replay the video for you. I would like for you.
Wait, I'm going to pause her video for a second, but I want you to send me in the chat what are the two quantities we're talking about, all right? She just said it, but what are the two quantities we're looking at? And I'll continue to play.
To pause the video every 1 second and record the diver's change in elevation after each 1 second interval. Once you have recorded his change in elevation over each 1 second interval, then I would like for you to represent it in a graph using your graph paper. Now that you've had an opportunity to create your graph and table of the diver's change in elevation over time, let's take a look at what I've come up with and compare your work to my work. We can begin by considering his initial elevation. What was his starting point? We see that at the 48-second video timestamp, the jumper's elevation was 36 feet. After advancing the video 1 second, we see that at 49 seconds on the video timestamp, the jumper's elevation was 35 1/2 feet. After 50 seconds on the video's timestamp, we see that the jumper's elevation was 30 feet. After 51 seconds on the timestamp, we see that the jumper's elevation was 25 feet. At 52 seconds on the video's timestamp, we see that the jumper's elevation was about 7 feet. And then right before the 53 timestamp video mark, at 52 and 75 hundredths of a second, we see that the jumper splashes into the water, so his elevation is 0 feet. And then when we graph this on our graph paper, here's a nice representation of what our graph will look like.
And I'm going to pause again at this point. So it shows the elevation on the right, which is the y-axis, all right? And then it shows the time on the left. And all she did is she just played the video and slowed it down. And they already told us that it started at 36 feet. That's how high you jump from. But I want us to put in the chat which variable or which quantity is independent and which quantity is dependent. I want us to look at that. And then the other part that I want us to look at, so that what I said just now, put that in the chat and tell me which is independent and what's dependent. But what I also want us to look at is all she's doing is matching the graphs. So she'll go on the seconds graph and look for 48, right? 48 seconds. And then she'll match it with 36. And then so it's just matching the numbers, putting the dots in, and then scrolling, attaching the point, sorry. So after you create your dots, then you'll attach your points. So we're gonna continue. If you have any questions, put in the chat, because remember, this is being recorded.
So did it take the jumper 5 seconds to fall before splashing into the water? When we equate the video timestamp seconds to seconds, we see that that is almost 5 seconds. When we previously watched the video clip, we were watching the jumper fall in slow motion. This time, I'm going to replay a clip of the jumper attempting to fall, but we will be watching it in actual time. As I replay this video, I would like for you to count the number of seconds that it actually took for the jumper to fall before splashing into the water. We see that it only took the jumper 1.5 seconds to fall before splashing into the water. So then how do we correctly graph the jumper's fall? As we begin, we can first look at the graph that we originally created together. We can note that in this graph, we know that the time that he started was at 0 seconds, and his elevation at 0 seconds was 36 feet. This time, we will use a similar graph, but we know that the length of time that it actually took the jumper to fall was only 1.5 seconds. So as we begin to make a graphical representation of the jumper's fall, we see that it will look similar to this. When we're just looking at our graph, it looks like we have shrunk or condensed the x-axis. So it is safe to say that we can condense or shrink the x-axis until the t-intercept, or the amount of time it took the jumper to fall and splash into the water, is equal to 1.5 seconds. Take time to go and rewatch the video of the jumper's actual fall. As you're watching this video, pause the video so that you can record the jumper's elevation over actual time. I've created a table here, and your table will look similar to my table. I have noted that at 0 seconds, the jumper's elevation was 36 feet, the same as it was in our original graph. However, I paused the video at 33 hundredths of a second, and at 33 hundredths of a second, I noted that the jumper's elevation was 35 feet. I paused the video again at 7/10 of a second and noticed that the jumper's elevation was 30 feet. When I paused the video at 1 second, I noticed that the jumper's elevation was 24 feet. I paused the video at 1 25 hundredths of a second, and the jumper's elevation was 15 feet. And then when I paused the video at 1.5 seconds, I noticed that the jumper's elevation was 0 because that is when the jumper splashed into the water. In this lesson, we graphically represented a real-world story that involved a change in elevation over time. We also explored a real-world situation of when it's relevant to shrink or condense the x-axis. When we take a look at this graph that we just created in the lesson today, we can quickly notice how this graph looks different from the one that we created in Module 1, Lesson 1, because this graph has a curve. We can also draw our x-axis and reflect this curve over the y-axis and create an example of a graph of a quadratic function. When you were in 8th grade, you saw the graphical representation of area equals side squared. And that graphical representation looks similar to this graph here. Throughout this year, we will continue to study graphs of quadratic functions and their equations so that we can learn different ways to recognize and represent them.
I want us to recognize, let me go back a couple of seconds. So we want to look at this graph. When we're looking at the graph, he was up here, but at what part of this graph do you think he was going the fastest? At what part of this graph do you think his speed was at his max when he was? So I'm going to label this part, the first part 1, the middle part 2, and the last part 3. So put in the chat 1, 2, 3. What part do you think he was going the fastest? Is it the first part, the second part, the third part? 1 is at top, 2 is in the middle, 3 is at the bottom. So the first part, he was very stagnant, right? And he was just standing there waiting. And then he jumped and picked up some speed. And then he was accelerating even faster and faster and faster. And then he stopped. So he was at his fastest during the middle part. So the second to last part of the option. Yes, I saw that in the chat. The second to the last part right here, that's when he was at his fastest. All right. Yeah, that makes sense, right? Because he started, and then it's literally like you're starting a car and you have to build up your speed, and the moment you're getting ready to stop, you slow down. So the middle part becomes the peak of which you start going through. But that's that video. I hope we were able to just understand how these quadratic functions work. So we looked at linear functions and we looked at quadratic functions. So a lot of times when we look at graphing stories, they don't always have to be linear. They don't always have to be straight line. They could be nonlinear, and a nonlinear graph is a quadratic function, all right? So it's just, again, I want to show you an example of what a quadratic function is. If you have questions about this, let me know.